Hi, everyone.
Здравствуйте.
И снова здравствуйте. Так. Okay. So our next topic is SQL, structured query language. And so the structured query language in earlier versions called structured English query language is aimed at making easier query formulation. So that's a family of standards, and the last standard is from 1997 or 90, something like 20, 11. Oh, let me check. So here. Let's look at this. So SQL for Wikipedia is the last one is SQL for 2008, but that's not right. Yeah, here it is. The last is from 2016. Maybe I can find a standard. Let's switch to English version. Syntax and so, and yes, the very first standard is from 1966, and then most popular most popular is 92, SQL 92, and then newer versions added regular expressions, recursion, triggers, and then stripe them off. Then XML features, and then something, and temporal data for SQL 2011. And the last, not last, yeah, from 2019, multidimensional arrays, but probably no vendor support anything but 1999 or just 19 just next version. So we have multiple standard versions, and for the last 20 years they only add special things like legalize order by outside cursors or something, some different ways that how SQL can be used with XML, just temporal data, just single statement, single closure period for, and some enhancements. So So standardization is on its road, but we don't need it too much. So our database, how to convert it into SQL, how to convert it into data definition language of SQL. Having this interrelationship model, then logical model, relational model, as names for this tables with relations, attributes or columns, and some. So we need to go to implementation, and we try to create implementation of this table or data. So SQL allows to define data, to define a table. Since SQL, we need to provide data types first. And some of the data types are common for all the vendors, and some are standard. And standard say we have character varying and something else. But most common data type for strings is var character, variable character, varchar, and with length, with maximal length. Numeric and decimal data types, and integer data types for long int, big int, small int, and so on. For dates and times, different vendors still has different data types for even for dates and times, and we need to working with date and time. We need to have too much attention to details. Anyway, create table is just simple statement. Create table, name of the table, then round brackets, field name, data type, space, field name, space, or multiple spaces, multiple white spaces, then data type, then space or multiple spaces, and then additional details like not null, this field must not be null, or default value, or check condition, or foreign key, or primary key, some additional things or options. After table is created, if we have a table, we may drop it or delete it. So drop table is a command to drop table, not only metadata, together the metadata and data and user data with all the body, with all the records. We may modify structure of a table, and arguably that's the most, that's a SQL operator that has largest list of options. We may add columns to table, we may change columns, we may drop columns, we may add restrictions and remove them and do multiple different things. Add column is just one of the possible options. And we may, for tables, so tables may be created, dropped, altered, and for special purposes, we may create indexes. To each index is an additional data structure stored in data files that allow to read or to perform some queries on this table faster, but not all the queries, and with no guarantees. So if I create an index on professor on, let's say, name and age, I may expect that my searches where with name set in a search and age set, I may expect that my searches will run faster than if no index is created. But that depends on multiple things. That depends on data skew, maybe. If all my professor has the same name, so no index will be of no use, and so on. And drop indexes to delete index. We'll look into indexing technologies and indexing methods, kinds of indexes in second module. Any case, in any way, database management system allows to remove or make redundancy and inconsistency smaller in our data due to normalization, and we'll get to normalization, and to provide automatical checks in some places. So inconsistency primary keys may solve some primary keys, foreign keys may solve some inconsistency problems. And declarative access to data, and maybe some special commands to synchronize data access, like locks, and to perform recovery and provide security and everything. So in most cases, database management system allows to reduce cost of doing something, to make something better, maybe faster, maybe cheaper, and but that's not the only way to reach our goals. So database management system is not a silver bullet, it's just a system that stores data more or less efficiently. It allows to search for it, allows to query it, allows to solve some concurrency issues, to recover data after failure better than if we have no database management system, and so on. So some of the kinds of integrity, of data integrity, of constraints, integrity constraints, are just keys, primary key, foreign key. Another constraint is multiplicities, so one to many, many to one, many to many, or attribute domains. So that's not just an integer, but integer, this attribute should have value from list of 2, 4, or 6, nothing else. That's attribute domain, or in some cases, just every string will go. Any string will go, and so on. And referential integrity, if I define foreign key for my table, that means that values in this column I define foreign key for need to come from key of some other table. So in some cases, some constraints like keys or domains, attribute domains, any instance of database management system must meet. So I can't add a record if I have a check condition for a column in a table that domain is greater than 5 and lesser than 10. Then I can't insert record with value of 11. So that's static constraint. And some of the constraints are are dynamic. So they are constraints on behavior, not on just values in database. And those constraints are for transactions mostly. So we'll not look at dynamic constraint at the moment. And in some cases, constraints may be implemented in the database. So database management system is in charge of checking it or enforcing constraints. And that's a good way to document everything. So we have a database and everything is built in. All the checks are defined on database level, and database is in charge of checking it. So database is a central point. So any client tools, including administrative tools, can't break our data. So if I tell that domain is this, then every kind of access will be checked for these constraints, for this constraint validation. So in some cases, some checks may be performed in my application, but in case I forget it, or some other team members forget it, or even other teams create another application to access my database. So checking constraints in the database is a safety net for all these cases. And checks in database allows for some optimizations. So if I may set constraints that all students are older than something, and then query like this is come, select all the students, where age is lesser than this. Query optimizer, knowing about constraint, may just answer no, empty set. So query can be evaluated without even looking at any students. With some constraints allows for some optimization of some queries, query elimination, and so on. And application, implementation of constraints is better for error messages. If I fill a form on a screen and then press a button to submit, then it's better for me to have meaningful messages, and that meaningful messages probably would go from application. Application check this and that and that and say, you need to set this, you might not set that, or something. Database will send me a technical error. Oh, no, primary key violation in table. Oh, what does it mean? Foreign key violation or some other constraint ABC 1, 2, 3 violation. Oh, what's incorrect? Well, what's wrong? So error messages may be made meaningful only in application, and database know about only uniqueness and other technical constraints, and it can't provide meaningful error messages. So it's important to do both, to check everything in database as much as we can, implement constraints in database and implement constraints in application too, but for different purpose. So one of the kinds of constraints is called referential integrity. Referential integrity are called foreign keys. Referential integrity constraints called foreign keys, and that's a reference to a tuple from different relation. Yes, so like in the lecture, we have person number, and that's a foreign key that refers to professor. Person number in lecture, the same person may deliver multiple lectures. So person number in lecture tables is not unique. So foreign key is quite controversial concept and term and keyword, as that's not a key. In most cases, key is something unique we may use to access exactly single record. Primary key is a key that's uniquely identified, just single record. But foreign key doesn't identify anything. It doesn't identify a record in table it's defined for, but foreign key refer to a single tuple with a unique key in outside relation, in a different relation. That's why it's called keys. So it's a key in a different relation, in a foreign relation for me. So referential integrity, every foreign key, either the value of the foreign key is null, that's completely legitimate, or the reference tuple must exist. So if a value in my lecture table, person number is 11, professor with person number of 11 must exist, record for professor with person number 11 must exist in table of professor. And null is possible value for referencing place. So I don't know who read this lecture. Person number is null, that's empty value. That's possible too. So how to define referential integrity? To define just keys, not primary keys and all other keys. We have unique keyword, and for primary key, and for foreign key. I'm sorry, just one moment. So, example.
I'm sorry. I have a question.
Yep.
You said that SQL syntax to declare foreign key is foreign key, but in create table S we have C integer references error.
Oh no, that's not.
It's not the case. I think.
No. Thank you. Foreign key. There is no keyword foreign key. I'm sorry. only references. We have no foreign key as a keyword. Primary key yes, unique. Here it is, and column references to table. That's not completely correct here. So we'll look to court examples. So references is a correct thing. So column here references that table and a column there. So that's no foreign key references. So if we update data that is referenced, so update reference data, that may result in some violation. So I have a value of 10 in a table, and in table R, I have the same value of 10, and that's okay. But what if I change this value of 10 into 100? What should I do with table S that's reference to this R, to this R table? So what if reference table is changed? I may expect that that update result in a violation of, so there is no value of 10 anymore, and in a reference table, and tables that reference other table that have references keyword in its definition, so that constraint is violated. So what to do? First way is to reject it. That's not, I'll have just an error. That's default way, reject the update. Second way is to cascade it. So if reference table is changed, then I need to propagate all these values upstream to tables that's reference to it. So if previous value was 10 and in referenced table I change it into 20, then I need to go to all those 10s and change them to 20. That's cascade. And set null, that's possible to have a foreign key being null. So instead of cascading, I may change it and just set null values for that. That are kinds of maintaining of relational integrity, maintaining or cascading. What to do, it depends on conceptual model. Let's say if we have weak and strong entities. So weak entities refer to strong ones. So weak entity doesn't exist without strong. So we may just reject it. So default behavior, we don't allow we don't allow to remove strong entities if there are some weak entities that reference them. You need to remove weak entities first, and then you may remove strong entities. That's one way. Or if we change strong entity, let's cascade it. All the weak entities are just children. If parent change something, change family, change last name, then all children need to change last name too. So that's another way to cascade updates to weak entities in case of changes introduced to strong entity. But in some cases, that's possible to set null. Let's say I have let's say I have orders that belong to sales managers. who created them. And that's referential integrity. That's a constraint that an order has a sales manager ID, and sales manager ID is a reference to table of sales managers. And then people who created this order is fired, and we remove all the records from all the tables. We don't want to remove his order, or order he created, but it can't reference to this sales manager anymore. So we just set it to null. We don't know who created it, and that's okay for us. So in different cases, we may prefer or choose different ways of default, rejecting, cascading, setting null in different cases. So let's look what's happened. We have table S, and table S refer to table R. And we can say update R, set A equal to A1 next A1, where A is previous version of A1. Or delete this record. So that's just an operation that we want to cascade somehow, or reject it, or something. So in case of S update, table S has a column of A that reference to table R to column of B on update cascade, or delete cascade. So on update of R, new value migrate here, and all the A1s will be changed. In case on delete cascade, if record is deleted in reference table, then all the records that are referenced in all tables, in all records in table S will be deleted too. So update cascaded to referenced back reference, and deletes are cascaded too. Set null on update, set null, or on delete, set null. So A1 is changed, everything that's referenced to it is just set to null. In case of delete, there is no record of A1, and all that reference to it set to null. So let's skip this picture and go to final description. Final description. Oh, yeah. So we have professors, we have lectures, and students who attend lectures. Let's look at table lecture. Lecture references has a person number that's references professor. If professor is fired, on delete cascade, so no lectures may be delivered by other professors. If professor is fired, no lectures of this professor. So we delete records upon removal of professor record. We delete all the lectures delivered by this professor. Attends references lecture on delete cascade. If lecture is deleted, then all the attendance records of this lecture need to be deleted too. So there is no meaning in the record that student A attended lecture number 10 when no lecture number 10 in our list. So on delete cascade is adequate here. And constraints on domains use keyword check. Let's say field of semester need to be between 1 and something, or semester is greater than something, or field in a list, semester in list in round brackets 2, 4, 6, or level in a list of strings or something. So check is quite simple. So let's look to create tables for university database. Student, stud ID, integer and primary key. Oh, sorry. So name, so stud ID is an integer with primary key, and name is varchar of this maximal length of, sorry, not empty. Primary key is not null by default. We can't have primary key empty, and name too. And semester is an integer with check, but it may be empty. We said no, not null, and only values in case of value present. Professor, integer primary key for identifier, name, level, that's 2-character string. This check of level might be this or that or those. And room is an integer, and that's unique. So each professor has its distinct room. So we need, and professor's primary key is person number, but room should be unique. We aren't allowed to put some professors in same room. Then assistant, person, name, area, boss is an integer, and it's nullable. Some assistant may have no bosses, and area is nullable. So some assistant may have no area field. And boss, that's another way to describe. So first option is online referencing, like in lecture tables, and person number of integer references this table, and then on delete, let's say set null. And another option is define all the fields, and then after comma set foreign keys, primary keys, and some other constraints. So here we may use keyword foreign key, that boss references professor on delete set null. And here we have primary key outside of field list, as primary key is compound. Student ID is an integer, and that references student. Lecture number is an integer that references lectures, and on delete cascade. And primary key is a combination of student ID and number. So I can't say primary key here and there. The only place is here, after comma, primary key, and list of IDs. Requires the same thing. Prerequisite is an integer references lecture. Follow-up, integer references lecture, and primary key is combination of prerequisite and follow-up. And the last thing, tests. Student ID references student, number references lecture, person references professor, and grade. That's numeric, and we check that grade is between in some interval, some value interval. And primary key is here. So that's definition of our table, our tables in a database for university. How to put data to tables? We have insert operator or command, and the form insert into table name. And one option is select some query that and query result will be inserted to table. And other way is a literals list prepended with keyword values. So insert into student, stud ID and name, that's list of fields, space, values, keyword of values, and in round brackets, values for fields. That's insert. And result, if I insert for student with name, this number and Archimedes, then semester is not set as possible. Semester is a foreign key. References, oh no, semester is just an integer. This not null condition. So that's possible to be null. And that's it. Let's keep Oracle's automatic increment. In different systems, we have sequences and special methods to generate automatically IDs. So looking in in different vendor systems will use it. Updates. Other operators. To delete tuples, we say delete, then table name, and then condition. If I skip condition, so I may run just delete student, and that's all. Delete student lead to delete all the records. So where limits what should be deleted. So only semester greater than 13 should be deleted, and all others should be retained. Delete without condition effectively clears the table. Delete all the records. Update student, that's making updates to records. And after keyword set, I say how to update it. Field name equal to some expression. That's not one way to use for increment. I may use this one, but expressions are not limited. I may even put subquery here or something complex, or constant, or another field, or another field +2, or something. So any expression that return just single value for each record is allowed. So how to query after data is put in a database? We need to query it. And the simplest kind of the query, well, not the simplest, all the queries start with select keyword. And select is not for, that's not keyword for selection, but for the queries. As SQL tries to be as English-like as possible. So I may read this, select something from table something, where some condition. So that's maybe read quite fluently and easily. So after select, we have a list of fields, a list of columns. After from, we have table name. And we may stop here and just select everything, all the records from professor. But if we add where, then we add a predicate, a check. So select will return all the records where level is equal to this. We may sort our results, select something from table and order by level in descending order, and then name. So all the results will be sorted by descending of level, and then ascending of name inside a group of records with the same level. In some cases, we do want to eliminate duplicates. And to eliminate duplicates, we need to use distinct keyword after selection, as duplicate elimination is quite costly. So duplicate elimination may be performed by grouping, by hashing, by sorting. Anyway, it takes additional operations. So that's why they make a special additional keyword instead of building it into select keyword, into select keyword behavior. So we don't want to check duplicates every time we output something. So the tables are here and the queries. Let's look here. I want to find who read the lecture of Myotic. I need to loop through lecture table, find what I search for, and then have a value for person number, go to professor and loop through this professor table, and I find this number, so I have Socrates. So how to answer question who teach Myotic? I need to perform loops from in one table and then nested loop in another table. Let's join. That's a join operation, and it may be expressed in different ways. Simplest way is to list all the tables that should be joined, professor, comma lecture, comma something, and then provide conditions. person number from professor should be the same as professor number from lecture, and lecture title should be this. Anyway, that's equivalent to this relational algebra expression: professor, Cartesian product, lecture, selection on conditions, all these conditions, and then projection on a name. So how this may be evaluated? So I have two tables and then Cartesian product of them. I have, let's say, 7 records here and 20 or something records there. So this table has 7 multiplied 20 records. And then I go through this table and search for, oh, here it is, my edit, and search for correct pairs. Person number here, prof number there, are different. And here, professor number and person number are the same, and title is medic. So great. Go to intermediate result. Send it to intermediate result, and no other result. So result of selection from Cartesian product is this, just single record, and then projected, and name is this. We may join multiple tables in just single query. Anyway, all the Cartesian products are binary operators, and we need to find Cartesian product for 2 tables, then Cartesian product with the result of previous operation, first step and 3rd table, and so on and so on and so on, and then apply selection conditions and then projection, and that's it. Optimizers may choose order of Cartesian products. They may push down predicates, some predicates down, push some predicates down this tree. If I have a condition that may be checked for R2 relations, then I may push part of predicates that check conditions with R2 down here. That would be efficient. We may add 4 tables in a list of from. We may add aliases, so student S, attendance is A, lecture is L. This is just another names that we may use to refer to tables. So instead of student, we may use S. We may rename attributes, essentially add another aliases, a person number as prof number. So and result will contain this field. Set operations are simple. They just have two selects or more, and then put union or intersect or minus between them. And the last most important keyword is group by. But first, let's look at aggregation. And aggregation is calculating an aggregated value for the whole table here. So loop through the whole table, all the records, and calculate average value for semester on finding maximal value or counting records, or calculating sum, and so on. But that's a calculation aggregation for the whole table. In some cases, we want to divide the whole table into groups, and each group should have the same values for this group by what? By this field. And then we may output for each group. Each group consists of multiple records from table, but we'll never see them. Instead, we'll have, as a result of this query, we'll have just single record for each group, 1 record per group. And that record may contain values we group by, so person error is we may send to output, and all other fields need to be put under aggregation function. CP, maximum CP, average CP, count of CP, sum of CP, All of these are possible, but no select person R, comma, CP. As in a group of records of lectures with the same person number, there may be different CP values. So you need to find a unique value, just some single value for the whole record. And we may add condition for group filtering, where filters records, that checks for records, where record field level equal to this, or where field of person number from here equal to person number from there. So we compare just fields in single records from base tables, then group, and then for each group we may calculate another aggregation function or the same aggregation function, and then check it. So I have a group of all the lectures for given person, and then I calculate whether average points for that person is greater than 3. If yes, then we'll add this group to final output. If not, then we'll just drop it off. So having, and we can read it, select something from tables of this, where conditions are met, group it by these fields, and output only groups having these values, having average of points greater or equal than 3. Now let's look at data. Lecture from lecture and professor. That's Cartesian product. All the combinations of lectures and professor. And here, lecturer is this, and here we have just professor, a number of that. So that's Cartesian product. That's not a joint. It's all the combinations. Each lecturer is each professor, and then we find combinations with the same values. So for ethic, we have the same number, so that's Socrates. For Grundzüge, we have person numbers for Kant. For Maidic, we have Socrates one more time. For and so on and so on. And then we group it. If we want to group it by person number, so we have a group for all the lectures by Socrates, all the lectures by Russell, and all the lectures by Kant. But we'll never see a table like this. If I want to see this table, I need to use, instead of group by, I need to use order by. And then all the records come to an output ordered by person number. So effectively the same thing. But if I want to group it, then I use having, and having retain only first group with CP average on CP greater than 3. Second group has average of CP lesser than 3, and the last group. And then to output what I want, I want person number, name, and a sum of CPs. So 20, so Socrates and 10, and Kant and 8. So that's it. Socrates and 10, Kant and 8, and so, oh, I'm sorry, one moment, please. Okay, let's go. Resume. So, additional things to select, where, group by, having. In where, we may use additional, we may use subqueries. First of subquery kind is exists subquery, and exist means that its argument is not empty. That's a table, and if the table has at least single record, then exists return true. Exists returns true. So what we have here, that's essentially the question. I want to find all the professors who has no lectures, without lectures. So for logic like this, so I want to loop through professor, and for every professor, I run this query, substituting professor number here, and that's called correlation. So I have current record in my loop for professor, and I get a single value for professor number, substituted in selection, in internal query, in subquery, and then executed. If result is empty, no lectures delivered by this professor, then exists will return false. So exists, no. Records table doesn't exist. But not exists, return true. So this professor go to professor name, go to final answer. So every professor that has no lectures, at least that has no at all lectures associated with that professor, all the professors go to final result of this query. And if a professor has at least single lecture, then that select return at least table with at least single record, exists return true, not exists return false. So this professor should not go to result. So that's it. Other way, so that's called correlated subqueries. And correlated subqueries are not as fast as probably, not probably logically. SQL implementation need to loop through all the records of first table and re-execute subquery multiple times. If I have hundreds of professors, then I need to execute this query 100 times with different professors' values, and no caching will help. So I'll have just different sets of lectures. So even if I cache them for another professor, I'll have completely different set of lectures. Other way to express this same intention, to achieve the same goal, I may run uncorrelated subquery. So I have subquery 2, and that subquery is not correlated with external query. So what's correlation? Is referencing to a table. I have a table of P, professor P, and I refer to professor to table P. If I have no references to outside table, so that's subquery. That subquery is uncorrelated. So select person number from lecture. That's a list of all the person numbers, all the professor numbers who deliver lectures, even with duplicates, but I don't care. And then I loop through professors and search for professors whose person number not in this list. That's a list of professors who deliver lectures. So result is a list of professors who don't deliver lectures. Uncorrelated subquery probably is better than correlated, as I run this query only once and have just a list, and then I may cache it and use for every professor, or not just cache, but I may convert it into a hash table to search faster in this list or something. In correlated subqueries, almost no optimization ways to optimize it naively. If I execute it, here I have a loop, and here I have another loop. So I need to, I have nested loops, and I need to run them. But let me find, yes. this slide where we rewrite. Essentially, I may, or optimizers, not that me, that's optimizer, who may rewrite some queries, this exists, in terms of joins. Let's look at this query. Select all assistant data of such assistants who are older than their respective professors. So for each assistant, I try to find such a professor, so maybe professors, so that assistant, that's professor, his number, this professor is a boss for current assistant. So that's a loop. I have a current assistant, substitute value here, and search for professor who is boss for that person. And one more condition, that professor's age should be smaller, lesser than assistant age. So I substitute both values for a boss and AH here, and then run this query. And if this query is empty, that means that either that assistant has no boss, that's possible too, or assistant has a boss and boss age is not smaller, not lesser than assistant's age. So empty result means that's not, that assistant is not what I search now, so I don't output it. And if I can find a professor who is younger than his assistant, then exists return true, as at least single record is here, exists return true, and assistant go to answer. Equivalent query in joins is the same. I try to combine all the assistants and professors, so with the same condition. So assistant's boss is exactly this professor. I find pairs and then compare their ages. So if a professor is younger than assistant, then okay, output all the assistant data. Exactly the same, exactly equivalent results. So queries are equivalent. For every imaginable database, the result will be the same. The first query return, let's say, assistant 1 and 2 and 3. This query will return assistant 1 and 2 and 3. So if for some database it returns none, this query will return none too. So that's a query rewrite that happened under the hood in SQL engine, but we may expect that it will happen. So we may write this way or that way. And what's the difference? Join query is more suitable for optimization. There are too many methods of join optimizations, different methods of join execution, different ordering of tables, different indexing, and so on and so on. And exists, if we try to optimize this, the top query here, well, how can we optimize it? We have a selection, so we may just read the table in order and check something, and then check, and that's essentially a nested loop. So almost no ways, no methods for optimization, direct optimization here. But this query rewrite idea, we change form of the same query, we change the query in equivalent one, and then all the optimization methods are available. So we may employ this, apply that, and so on. Let's keep all subqueries, and subqueries in select and from may be utilized too. So subqueries mostly utilized in where, so I put it here, and in where I may use subqueries under exists, under in, or under some other functions, and even I may just compare and think that select something from something equal to something, right? I need equal to 10, let's say, but I need to be sure that my selection return exactly a single record and a single with a single column. If not, then I'll get error on execution in runtime. So exists is more safe. So if I check for existence, okay, empty table, empty select result, or not empty, I will never get an error. But if I try to compare, where checks for conditions for predicates? If I try to compare selection with something, and selection is a table, I can't compare it with scalar value. So, and subqueries may go to selection list, select this and this and that selection. The same condition. I need to be sure that only single value is here. Not single value, but single record. I may select this and that and that and that and go here. But single record of that subquery. The subquery need to return. Or I may put subquery here in from clause as just a virtual table. So that's a table. Every selection result is a table. So I may use it in another query in this way. So that's possible. That's possible too. So query rewrite. And yes, SQL doesn't support division, relational operation of division. So we need to play tricks. And let's look at how it can be implemented in SQL. So we've seen how to implement different relational algebra operators like joins, unions, and so on. Not implemented, just formulated, defined. I want to find students such that there is no lecture with CP equal to 4, such that no attendance record for the student and that lecture. What does it mean? I want to search for student who attends all the lectures of CP of CP of non 4. So if I can find, let's look here. I have a student, I have a lecture. So first loop, second loop, and third loop inside. For each student and each lecture, I try to check for attendance record. And what if I can find it? So the student attended this lecture. Okay, this selection returns something. So not exists return false. It do exist. Attendance record for this student and this lecture. Not exist false. And where something and false, so that's false. I don't care for other conditions. So this selection for each lecture return nothing. As where evaluation condition under where evaluates to false. That means don't output it. So result is empty. In case if I can find for student lecture attendance record. So result is empty and not exists is true. Okay, so student with at least one lecture. So if a student attends one lecture, not exists attendance record, that's false. Select is even single record here. When not exists became true. Not exists became true if no records here. So if a student didn't attend this lecture, then not exists is select of star is empty. Not exists is true. And let's say that lecture is has points of 4, then this selection is not empty. So lecture is output is in the output if this lecture is not attended by the student. So essentially, all the lectures will be here that are not attended by this student. So if if I have at least one lecture that's not attended by student, that selection is not empty, exists as false, exists as true, and not exists as false. And then student is not part of my result. If at least one lecture, that is not attended. If all the lectures, are not attended by student, then here I have empty set, exists as false, not exists as true, and student go to a result. So probably that's not correct implementation for the query I have in mind. Let's look at another query. Select all the students from, let's say, table of attendance, group them by student ID, and I have for each student a group of all attendance records of this student, and then check. I can count all the lectures. So I have all the lectures that number of lectures that are attended by this student. Let's say 10. And then I select all the counts from lectures, all the lectures from the list. Let's say 20. So group of 10, 10 is not equal to 20. So student is not part of my result. But if some student attended all the lectures, then count is, let's say, 10, and list of all the lectures contains 10 lectures. So 10 equal to 10, and having allows to output this group. So essential query for searching of student who attended all the lectures. And I need to say that for each student, I want there should be no lecture that he not attended. So no lectures, no lecture that's not attended by this person. So I don't need such a two. So I'm sorry, I need to change it. And if we consider only special lectures, then we may add conditions here and there. So that's a simple way to express using grouping the same thing, but that's possible to express in this multi-layer things. So let's stop for today, and next time we'll go further and look at nulls and something else, but I think that's enough for today, and I need to correct this query too, to make it better. I'm sorry. So,
All right, thank you.
Yeah, thank you.